Uh, Good morning, good afternoon, and good evening, everybody. I'd like to talk about computational advertising. It's a new field and it is highly statistical. The online advertising market is currently valued at $309 billion, and it's projected to go up to $982 billion by 2025. And it's the major revenue stream for a batch of IT companies, including Google, Facebook, Amazon, lots of places. One component of computational advertising is online ad clicks. So when you type pizza into your browser, it triggers a virtual auction that lasts about 7 milliseconds. And various pizza companies, Domino's, Papa John's, Pizza Hut, all bid to show their ads to your eyes. And these bids are weighted according to the qualification of the different companies. So mainstream companies that are well regarded and have a track record of integrity and performance, they get a markup. And a new company that hasn't been established and is very small might get downweighted. But this virtual auction occurs, and the highest bidder in this virtual auction, or this highest weighted bidder in this virtual auction, gets to show you their ads. Here is an illustration of how the online bidding system works, and I'll walk us through that, but I simply wanted to show that there are about 20 steps involved in bidding to show an ad to a person. So my browser contacts a publisher's website. So it might be CNN.com, New York Times, something like that. And the publisher's website then sends back content that includes placements that will need to be filled through an ad server. My browser then contacts the publisher's ad server to fulfill placements that will not go up for auction. So CNN.com might want to show an ad for one of their own programs, and that doesn't go for a bid, that just goes directly. And for things like that, where it doesn't go for a bid, the publisher's ad server sends back the information that it's going to display on my browser screen. But for other placements, there's other real estate on my desktop, and so those placements are going to be fulfilled by an exchange. And so the browser contacts the exchange with placement information and an indication on whether or not the placement should go out for a bid, or perhaps in some cases another private deal has been set up by CNN.com or some other agent. Now, if the placement, the position on the screen where an ad can be shown, is marked for real-time bidding, then an auction is set up by the exchange. And once the auction is initiated, demand-side platforms are simultaneously contacted to participate in the auction. And these all run in parallel. So Papa John's, Domino's, Pizza Hut, they have all worked with demand-side platforms to have them show their ads. And if a demand-side platform decides to bid, then it offers it sends the amount that it's bidding, and it also sends a tag, which is used to track the process. The winning bid from the auction and information on the bidder is sent to the exchange. The exchange returns to the demand-side platform an ad tag that contains everything needed to track the ad and the impression. That's whether or not you click on the ad, and the director log joins. And it's essentially a link to the director so that one can obtain user information and pass back the actual advertisement tag. My browser then contacts the DSP's director to obtain the ad server tag. The browser receives the ad server tag, and the browser uses the ad server tag to contact the advertiser's ad server requesting that advertisement, that image. So if Pizza Hut wins the bid, then my browser then contacts Pizza Hut to get the ad information. the advertiser's ad server returns all the impression assets and creative content to my browser. And if the campaign is using a third party for tracking, then that third party is contracted with the impression and the user information. And that's a way of keeping people honest. Pizza Hut wants to be sure that Google really is showing the ad for the pizza that they're providing. And a third party is a way of ensuring that Google is correctly identifying that the ad was shown. The third party sends back a pixel as a verification or a handshake token. The ad tag contains the JavaScript that the browser will show when the impression is seen, when it renders. And these signals are passed back only after the creative content is loaded, which is why these actions take place so far down in the chain. The DSP sends back a pixel as a verification, and the DSP's tracking pixel fires this information, and it's sent from the browser. So this representation of the complexity of the computational advertising process is still an oversimplification. There's a lot more that goes on, but this is the bare bones picture of how these online auctions work. But this is a fast-moving field. The ecology of e-commerce is changing rapidly. For example, it used to be that nearly all of these auctions were second price auctions. Technical term, it means that the highest bidder wins the auction, but pays the amount of the second highest bid. Ben Vickery showed that that was an auction that encouraged people to bid their true values as opposed to underbidding. But now these auctions are moving towards first price auctions in which the highest bidder wins and pays the amount of their bid. And the remarkable thing is that computational advertising touches on so many different aspects of statistics. It has to do with design of experiments, it has to do with causal inference, it has to do with recommender systems, predictive inference, and time series modeling. And computational advertising can also engage with text and sentiment analysis, dynamic network analysis, probabilistic ad contracting, spatiotemporal processes, censored data, and many other topics that statisticians know a lot about. And so I see this as an amazing opportunity for academic research, because I've got former PhD students who are now working in Google and Facebook and LinkedIn, and they tell me that their companies aren't really interested in academic research. They're fighting fires. They're not trying to find principled solutions. They're trying to do things that will get them a little bit more profit in the near term. Whereas academics have the opportunity to write papers and study things in general. And so I see that as being a mutualism that can pay off very well for both the companies and academics. One aspect of computational advertising that I find fascinating, and which is a workhorse of many CA problems, is recommender systems. If I go online to Amazon and start looking at books, Amazon is going to make recommendations for me about books that they think I would enjoy. And those recommendations are based on my entire previous purchase history and everything else that Amazon might be able to know or guess about me. And Amazon can know and guess a great deal about me. They have really good ideas about my age, my gender, my income bracket, and where I live. So if you're a human being and somebody asks you to recommend a book to them, well, usually we respond by saying, what types of books do you like? Do you enjoy murder mysteries? Do you involve historical fiction? Do you like science fiction? And so you'll talk with them a while, and then based on their responses, you'll make a recommendation that is tailored to their interest. And that is an example of an active recommender system. And currently places like Amazon don't really do that. But I can easily imagine that one day I will log into Amazon and Amazon will tell me, David, no matter what, we're going to make book recommendations for you. But if you allow us to ask you 5 questions, we'll do a much better job suggesting books that you will actually like. And so this is rather like playing a game that in the United States is called 20 Questions, but it has specialized features. Amazon, in principle, has a prior distribution over me buying any book that they have on offer, and that will be based upon some sort of Bayesian analysis. There are complexity constraints that we need to consider, and there's some non-standard feature selection. And one would need to build a proximity matrix for books that says, oh, I don't know, all the Flashman novels are sort of similar, or all 3 Lord of the Rings books are sort of similar. So they're near in proximity space, but other books might be very far away. So the usual approach to trying to determine nearness in book space is based upon either collaborative filtering or content-based filtering. Collaborative filtering looks for people who have bought the same books that I have, and then will make suggestions based on the assumption that those people are like me. Content-based filtering is a different approach. It says, if David has bought historical fiction before, then we will recommend historical fiction to him going forward. We should probably not have a single proximity matrix for everybody, because people will have different senses of what books are near to each other. Some people will follow specific authors, others will follow specific genres, and other people will follow what the New York Times Book Review recommends each week. And so this model space is going to be weird and non-Euclidean and individual. And so we're going to need to come up with some non-Euclidean way to determine nearness. And the statistical tools for doing this would be things like isomap and paramap. The next thing is that Amazon needs to decide what questions it will ask me in order to learn the most that it can about my taste in books. And unfortunately, the best questions it would ask are things like, on the whole, do I like these 100 books more than I like this other list of 150 books? And that's just too complicated a question for me to cognitively process. So there needs to be a complexity penalty on the types of questions that get asked. And so it might ask, I don't know, do you like fantasy novels with footnotes? And if the answer is yes, then it'll take me down Lord of the Rings, the Silmarillion, that path. And if the answer is no, then it will take me down a different path. And ideally, Amazon wants to ask questions that it has that its prior for me gives me a 50-50 chance of answering yes or no. Because if it can ask 50-50 chance questions, then it will learn the most as rapidly as possible. But there's a hidden optimization problem. The first question that Amazon asks might have a 50-50 split, but depending upon the answer, subsequent questions might be mostly 90-10 splits. And so you want to optimize this question tree that Amazon would ask. It might be better for Amazon to ask an initial question that has a 60-40 split if underneath that question, there are lots of other 60-40 questions that Amazon could answer. And this is a general class of problems, and I'm not aware of any previous literature that really walks through the problem in the way that I described. But it's terribly practical, and it could improve the value of recommender systems. And I will note as an aside that recommender systems are not just about recommending books on Amazon. Recommender systems are also used to drive the demand side platform's decision about which ads to show to you. They'll look at the text that you've typed into your browser, and should they be showing you pizza ads, or should they be showing you ads for vacation getaways in Italy? And that's a recommender system problem too. Another aspect of computational advertising is the way ad contracts get written. One financial model is that a company contracts to show a client's ads to, say, 100,000 women between the ages of 20 and 40 who live in California between January the 1st and June the 1st. And then they write another contract that promised to show a different set of ads to 200,000 people between the ages of 20 and 50 in Northern California between February and September. And obviously, these audiences overlap. So the company can try and decide when a person who could fulfill either contract logs in, whether to show them the first ad or the second ad. And one wants to have some principled way to try and decide which ad to show somebody based on how close you are to the deadline for the contract and how much of that contract you have fulfilled. Because typically, if a contract is not completely fulfilled, then Google or whoever the company is has to pay the advertiser a small amount of money to represent the lack of complete fulfillment. Also, Google knows a lot about people, and it may be able to infer age, gender, and where you live, and satisfy the contract based on that inference. So I can imagine in the future that ad agreements might be written to say that an ad must be shown to 100,000 people who have probability 0.9 of being women between the ages of 20 and 40 who live in California. And that would be a totally new type of advertising contract, but it would open the door to potentially a lot more ad revenue. And such contracts would be novel, and they would require third-party verification of the probability estimates. If Google decides there's a 90% chance that the person looking at the screen is a woman between the ages of 20 and 40 who lives in California, that's great. But Google has an incentive to overestimate the probability in order to fulfill the contract. So some third-party person is going to have to verify that Google's estimate is in fact reasonable and accurate. And as I mentioned, Google can guess users' age, gender, marital status, income bracket, personal interests with pretty good accuracy. And lots of other companies online can do this too. Dynamic network flows are an interesting aspect of computational advertising. Viewers log into the internet and then traverse a website. So it may be that I'll go to Fox News and I will click around on Fox News's subpages. So I'd look at sports news, I'd look at international news, I'd look at local news, that kind of thing. And you've probably noticed at supermarkets that when you are in the checkout line, there are racks of candies and pretty stupid magazines there. And that's because grocery stores have learned that people make impulse buys on their way out of the store. And so they put all those temptations there at the end. In terms of computational advertising, this means that they would like to be able to predict when you are about to leave a website. And that's the point at which they want to show you an ad for something that might be tempting. So I and a couple of other people examined data flows within the Fox News website. We used a decoupled recoupled technique to find Bayesian time-varying estimates of traffic, which is essentially something called a dynamic gravity model, and the reference is there. But basically, we are looking at flows within 22 sub-websites of the Fox News system. The size of these circles are logarithmically scaled indications of how many people are on that website at a particular time. And this will vary over time, of course, but you'll see that the home page is very popular. Then we also see that a lot of people are going to the United States. A lot of people are going to entertainment. A lot of people are going to website 11, which is world news. That's how people are flowing through this website. And we have tools that allow us to do process monitoring and change point detection. So we can see that there are different patterns for different Mondays and different Tuesdays. And they're similar, but not identical. So these are the estimated transition probabilities from the Fox News homepage to the entertainment page on 6 different days over the course of about 2 hours. Process monitoring is also important in tracking an ad campaign because you want to decide how much ad buy is appropriate over time. If you're showing an ad that's been around for several months, perhaps it's gotten stale and it's time to take that ad down and replace it with something that's fresh. And this is a tricky modeling problem because it's not just process monitoring. You have competing advertisers who are all putting in new ads and taking down old ads on their own schedules. And so this is a changing, evolving environment. And so you want to monitor the success of your advertisements in a world where your competitors are changing the ground under your feet. So that leads to interesting modeling problems. And we could imagine using tools such as the Cox proportional hazards model or adaptations of Mark Glickman's models for sports teams, because you can imagine that these are competing advertisers. And so something like a sports team model might be another way to try and address this. These will track changes in the click-through rate, and at a certain point, you want to change out your ad. Deep neural networks, especially generative adversarial networks, would be a potential tool for creating new ad content. Style transfer and other techniques would be useful. So you can imagine that you could take an old ad, use style transfer, and freshen it up. Or you might personalize an ad for somebody who tends to respond to cubism, but not so much the sort of Van Gogh style. Design of experiments is also a fascinating area. Google, Amazon, Facebook, Apple, and Microsoft run 10,000 and more experiments per year, and they engage with millions of users. LinkedIn reportedly runs more than 400 simultaneous experiments each day. And the companies use tools such as Optimizely and others to run and manage those experiments. And that's a whole important area of optimization. How in the world do you sort of control a lot of different experiments? It's a process control problem. You have lots of people in your company proposing experiments to a central source, and that decision maker wants to run those experiments in parallel, but not in ways that interfere with each other. There are a couple of recent books about online controlled experiments, and Netflix recently posted a job ad for someone who could support internal research into new methodologies for experimentation, as well as adapt existing methods, such as response surface methodology, to online A/B testing. Lyft used a 2 to the 2 plus a center point response surface design to decide what percentage discount to offer to customers who had not booked in a while, and how many such rides should be eligible. So they're getting very sophisticated with all this stuff. Companies experiment to improve on user retention mechanics, user acquisition funnels, user engagement, email promotions, website layout, aesthetic features, the checkout experience, branding, ad campaigns, and many other properties. And the workhorse for online controlled A/B experiments are getting much more sophisticated than the A/B name suggests. They're now using adaptive multi-armed bandits, and sequential experimentation has become common. And in many cases, the effect sizes are small, but they will translate into millions of dollars in revenue because of the volume of the product. In 2009, Google did a designed experiment to compare 14 different shades of blue for its hyperlinks. And they picked one, but I can imagine that in the future, they might create personalized shades of blue or personalized colors for hyperlinks. And I will note that some people have vision deficiencies in the blue spectrum. And it may be that for them, you'd like to have, I don't know, a magenta or an orange hyperlink. In 2008, the Obama campaign increased donations by 60 million by using a factorial design for the donations pages layout. So the page that I show you here, that was determined as a result of a factorial design that was done online. There are a batch of open problems in online controlled experiments. Typically, they only run for 2 weeks. So how can one estimate the longer term effects such as primacy? And that occurs when a change is good over the long run, but temporarily degrades performance. So you can imagine a new checkout interface that's more efficient than the old one, but you have to learn how to use it. And that cognitive load makes you temporarily unhappy with it. And maybe you're slower to do the checkout. The alternative effect is newness. And this is when a bad long-range change looks like it's good at first. So the initial experimental results say this is a good change, but in the long run, it's going to degrade performance, lead to less revenue, something like that. One also wants to estimate heterogeneous treatment effects by region or device or by gender. We know that network interference can violate the stable unit treatment value assumption in causal inference. So it could be that I see an ad, I tell my wife, she goes out and buys it, and we no longer have this independence of the experimental units. And then how do we manage information flow when a company is running hundreds of experiments each day? And there can be interference between 2 different experiments. I might see this, I might be involved in 2 different arms of an experiment, of 2 different experiments. And that's going to potentially lead to an interaction, and that could be a problem. So I will sort of close by pointing out some of the opportunities here. Computational advertising touches on lots of other aspects of applied statistics. Cluster analysis and multidimensional scaling should drive market segmentation and collaborative filtering. So if you want to identify a cluster of users for whom a particular ad or a particular product is really good, then you can do that with market segmentation. You'll identify people who have young children, for example, and so you'll be showing them ads for coloring books and baby food and things like that. Similarly, collaborative filtering is another way to try and cluster users, and that would be something that statisticians know about. Sentiment analysis and text analysis are also going to be important. Statisticians work with latent dictionary allocation, sentiment analysis, word to vect, natural language processing. Those are helpful in many ways, because if you're McDonald's and you're showing your ads online, you may see that somebody is sitting on a website that has a lot to say about hamburgers. And so you'd think naively that maybe this is a really good place to show an ad for McDonald's. But if it turns out that the ads that website is a pita site, then the sentiment about the hamburgers is going to be negative, and you want to flag that before you start paying money to show an ad there. Statistical tools for anomaly detection are relevant to lots of things, but cybersecurity is certainly one of them. And if you want an environment in which people are confident to click on an ad that you've displayed to them, you need to make sure that you're got good cybersecurity. You don't want people to find themselves clicking on an ad and getting exposed to some sort of phishing attempt or some other problem. There's a slang term called rickrolling, which refers to you click on a link and it takes you to something that's totally different. And that's a bad thing from the computational advertising business's standpoint. Spatiotemporal models can indicate when a coupon should be sent to a cell phone of a customer walking through a store. So some companies are imagining that they are tracking me as I walk through a grocery store. They see that I'm standing in the cereal aisle. This would be a really good time to send David an advertisement for Quaker Oats granola. And so I'll be sitting there, my phone will ping, I look at it, and I have an advertisement for a coupon to buy granola. So these are some of the possibilities that we can imagine going forward. I think it's a wonderful opportunity for statisticians, and I hope we will jump in on this. And now I'm out of time. Thank you all.